So we want to look at the effect of temperature on the resistance of metallic conductors. You see, a rise in temperature of a metallic conductor will also cause a rise in resistance of that metallic conductor. Now, the measure of the rate of change of resistance of a conductor due to temperature change is known as temperature coefficient of resistance. For pure conductors, actually, they have positive temperature coefficient of resistance, meaning that if their temperature increases, their resistance will increase, and if temperature reduces, the resistance will reduce. Unlike materials like semiconductors, for semiconductors, if temperature increases, their resistance would reduce, and if temperature reduces, their resistance would increase. That's for metal. So since like semiconductors, they have negative temperature coefficient of resistance. Now, we have the relationship for temperature coefficient of resistance, and is equal to R minus R naught temperature change. What then is R naught? R naught is the initial resistance of the conductor at 0 degrees C, and R is the final resistance of the conductor at the final temperature, either increased or decreased temperature. And then change in theta means the change in temperature, and then alpha is the temperature coefficient of resistance. Actually, this should be at 0 degrees C. At 0 degrees C. So let's make the resistance, the final resistance, the subject of formula here. That would mean if we cross multiply this, make this over 1. That will give us R minus R naught, that is, this multiplied by this is equal to alpha R naught change in temperature. And R will be equal to R naught plus alpha R naught change in temperature. And if we factorize R naught here, this will give us 1 plus alpha change in temperature. So that's that about that. Let's take some examples under this now. Okay, example 1 now. An aluminum cable at a resistance of 27 ohm at a temperature of 35 degrees C. Full stop. Determine its resistance at 0 degrees C. Take the temperature coefficient of resistance at 0 degrees C to be 0.038 degrees C per degree C. Actually, this is what it ought to be. Now, to solve this question now, quite easy. We are given that the resistance is 27 degrees C, 27 ohms, sorry, at a temperature 35 degrees C. Okay? Now, determine its resistance. I'm looking for its resistance, R naught, because resistance at 0 degrees C. 0 degrees C. So, we can say change in temperature here will be 35 minus 0, which is 35 degrees C. Okay, we are given our alpha, which I can call alpha naught, because that's the temperature coefficient of resistance at 0 degrees C. And that's at 0.0038 degree per degree C, actually. Okay, so let's go and get our R naught now. We know that our R is given as R naught into bracket 1 plus alpha change in temperature. So our R is given as 27 is equal to R naught into bracket 1 plus alpha 0.0038 times change in temperature 35. Okay? So let's multiply that now. So if we multiply this and add 1 to it, we are going to have 27 is equal to R naught into bracket 1.133. And then if we divide both sides by 1.133, we get that R naught is equal to 27 divided by 1.133. This will simply give us 27 divided by 1.133. That's 23.83 ohms. That's our final answer. Example 2, A carbon resistor has a resistance of 1 kilo ohm at 0 degrees C. And so the resistance R0 is 1 kilo ohm. That's 1000 ohm at 0 degrees C. That's our theta naught, 0 degrees C. Determine its resistance at 80 degrees C. So we're looking for the R at temperature of 80 degrees C. Now, our change in temperature here will be 80 minus 0, which is 80 degrees C. Our alpha naught is given as minus 0.0005 per degree C. And so we know that R is equal to R naught into bracket 1 plus alpha change in temperature. So our R naught is given as 1000 into bracket 1 plus alpha, which is minus 0.0005 times temperature change, that's 80. So this will give us 1000, 1 plus, multiply this with this, we are going to have 0.04. Minus, please. This changes to minus. So let's evaluate now. This will give us 1000 times 1 minus this will give us 0.96. So our answer will be 960 ohm. That's our final answer. In some cases, the R naught is not given. The resistance at 0 degrees is not given. What then can we do? We can have it that, let's say we have that the resistance at a different temperature, let's say that temperature is theta 1. We know that the relationship with this, with the initial resistance at 0 degrees C is given as R1 equal to R naught into bracket 1 plus alpha change in temperature. I'll call change in temperature 1. Because this change in temperature will be gotten from 0 degrees C to that theta 1. Again, also we know that the resistance at another temperature, theta 2, would be R naught into bracket 1 plus alpha change in theta 2. Now we can call this equation 1, and we can call this equation 2. Now if we divide equation 2 by equation 1, that will be R2 being equal to R naught 1 plus alpha change in theta 2 over R1 equal to R naught also 1 plus alpha change in theta 2. R naught will cancel out R naught. We will now have that R2 over R1 is equal to 1 plus alpha change in theta 2 over 1 plus alpha change in theta 1. This is the relationship we use. So let's have a question where our resistance at 0 degrees C is not given. So look at this question. A tungsten coil has a resistance of 12 ohm at 15 degrees C. And so that is, I called my R1. That is 12.0 ohm. And now our theta 1 is equal to 15 degrees C. Now our change in theta 1, here is equal to 15 minus 0, because I'm taking that we have a theta naught which is 0 degrees C. And so that will be theta 1 minus theta naught, which is 15 minus 0, and that's 15. Again, we are given, if the temperature coefficient of resistance of tungsten is, that's alpha naught, or you say alpha, 0.04 per Kelvin, 004, pardon, per Kelvin. And now we have to calculate the resistance, that's my R2, at what temperature? 80 degrees C. That's what we call theta 2. 80 degrees C. So I'm going to say change in theta 2 that will be theta 2 minus 0 degree theta naught also. And that will be 80 minus 0. And that's 80. And so we're going to use the formula R2 over R1 is equal to 1 plus alpha change in theta 2 over 1 plus alpha change in theta 1. And so I'm looking for my R2 over R1. R1 is giving us 12. Is equal to 1 plus 0.004 times 80. That's our theta 2, change in theta 2, over 1 plus 0.04 still times, this time around, our theta, change in theta 1 is 15, sorry. And so let's do this now. This is R2 over 12 being equal to 1 plus 80 times this will give us 0.32 over 15 times this will give us 0.06. And so now we are going to say there's a 1 here, please. So this is going to be R2 over 12 being equal to 1.32 over 1.06, and then we cross multiply. We have a R2 times 1.06 is equal to 12 times 1.32. And so making R2 sort of formula, R2 is definitely equal to 12 times 1.32 divided by 1.06. Let's evaluate. This is equal to 2.49 ohms. That's the answer for this question.